Okay, so our last topic of this semester is radiation. So we'll go through, actually, I think a pretty good discussion of radiation and give you enough tools to do some pretty sophisticated radiation problems. So this would include some introduction to Monte Carlo techniques, enough that you can think about at least view factors for surfaces, and then semi-gray calculations so that you can consider situations where surfaces have wavelength-dependent properties, right? So at the end of this, you'll be able to solve some pretty sophisticated radiation problems. But today we're just going to get started. So we're going to talk a little bit just about radiation. Radiation is kind of completely different than anything we've talked about yet this semester. We I've talked about conduction and convection, and to me, at least physically, it's pretty easy to understand conduction and convection, right? You have in conduction energy carriers that you can visualize, and they have a velocity that's related to their temperature. And so if the high temperature energy carriers are moving real fast and they hit a lower temperature energy carrier, there's going to be a transfer of energy from the hot or high temperature, fast moving energy carrier to the cold or slow moving one. And that's easy to understand. Radiation is a little different. So radiation is energy transfer due to electromagnetic waves. So if you remember what you learned in whatever physics course you took, or chemistry, I guess, molecules are always giving off electromagnetic energy as electrons move from one shell to another, or other types of transitions like that occur. And that electromagnetic energy is typically absorbed quickly by all the molecules around it. So if I'm a molecule in the middle of a material, and I undergo some kind of transition and some electromagnetic energy is given off, that electromagnetic energy doesn't go very far before it's reabsorbed by some other molecule in the same material, right? So that's not a net energy transfer, and that there's these interactions going on all the time. But if we are close to the surface and I'm a molecule and I undergo some transition, that electromagnetic energy has a pretty good chance of getting out of the material, and then it can go off through space and unimpeded go a long way, like a long way being all the way from the sun to the earth, for example, right? And so it can go for a long way before it's absorbed by some other surface, or the molecules that are composing some other body. And so we tend to think about radiation as being this surface to surface energy transfer mechanism, right? The surface of the sun transferring energy by radiation to the surface of the earth, or things like that, right? And that's kind of how we're going to think about it in this class, is energy transfer from one surface to another surface due to these electromagnetic waves that move through space. These waves are moving at the speed of light. At least in most cases, the speed of light is something like 300,000 kilometers per second. But they do have different wavelengths and frequencies, right? So they're not all created equal. They're all moving at the same speed, but some might have longer wavelengths and therefore shorter frequencies, or vice versa, right? So the wavelength and the frequency are related to one another by this equation here, right? The frequency is how many times per second the wave crests, right? And the wavelength is the distance between crests, right? So if I have a high wavelength, I'm going to have a small frequency. If I have a large frequency, I'm going to have a fairly small wavelength, right? And if you remember this equation from physics, it basically says that the high frequency stuff is the high energy stuff, right? The energy is related to the frequency directly. So as I go from very low wavelength stuff, that's very high frequency stuff, that's going to be high energy wavelength. And if I move up the electromagnetic spectrum to higher and higher wavelengths, I'm going to lower and lower frequencies, that's getting to lower and lower energy waves, right? So this stuff is spectrally distributed, right? Radiation, when we start talking about radiation, we have to think about how the radiation is distributed across the electromagnetic spectrum. This is just a one way of thinking about it, right? So here is my electromagnetic spectrum. I like to think about it in terms of wavelength, just because typically that's how it's thought about in heat transfer. If you go from low wavelength, again down here we're at high frequency stuff, that's really high energy stuff, all the way to high wavelength, right? This is going to be very low energy stuff. So down here you've got dangerous stuff, cosmic rays and gamma rays and stuff that will that cause damage at the cellular level if you're not careful. Out here you've got stuff that's not so dangerous, right? This is your radio waves and your TV waves and things like that. So we're, I guess the other band to point out here is the visible range of the spectrum. So the visible range is 0.38 to 0.78. This is all in microns, so 0.38 to 0.78 microns, 380 nanometers to 780 nanometers, right? We go down at the lower end, that's what we would perceive with our eyeballs as violet. The upper end is what we would perceive as red, and right in the center is green, right? So anything below violet, so anything down here is ultraviolet. This is this dangerous stuff, this high energy stuff. Anything above red is called infrared, and this is this less dangerous stuff, right? You have in this class, we're really only worried about radiation in the sense of stuff that will be emitted by a surface by virtue of its temperature, right? So I'm really interested in thermal radiation. I'm interested in, a hot surface emitting radiation that is then absorbed by a colder surface, and that causes a heat transfer. So that thermal radiation for temperatures that are, realistic really goes from, let's say, maybe 0.1 micron up to a little over 1,000 microns. That's the kind of range of the electromagnetic spectrum that we're going to be interested in. This stuff down here maybe is interesting in other classes, but this is really usually not the stuff we're interested in if we're worried about how much radiation one surface is going to transmit to another. So again, focusing in this class on heat transfer means that we're focusing on thermal radiation. If you really want to boil it down, we're going to think about a surface, and we're going to think about the net energy transfer from that surface, and that is always going to be related to, what's the difference between the amount of energy that surface emits and how much that surface absorbs, right? It's just in equals out, it's out minus in. It's just an energy balance, right? We need to do an energy balance on this surface to think about what's the net radiation from the surface. So those are the two parts to our problem, and we'll actually tackle them in kind of that way. We need to know how much radiation is absorbed by the surface. We need to know how much radiation is emitted by the surface. It turns out that this part of the problem here, how much is emitted, is a lot easier to think about than this part of the problem here, how much is absorbed. Because how much is absorbed depends on how much is hitting the surface. And how much is hitting the surface depends on what are the other surfaces that are in the vicinity, what are their temperatures, what direction are they pointed, how much of the radiation they give off will actually be intercepted by this surface. It gets to be a very complicated geometric problem to figure out how much radiation is even incident on the surface, and then how much of that is absorbed, right, depends on the surface. If I'm thinking about how much is emitted by the surface, that's really only a function of the surface, right? I mean, that's what is the surface doing, what temperature is it at, and how much radiation does it want to emit to its surroundings, right? We don't have to worry then about where it all goes if I only want to know about how much is emitted. So this is where we're going to start. We're going to start with how much is emitted by the surface. And the other thing that makes this part of the problem easier to think about is that there's this fundamental upper limit to how much radiation can be emitted by any surface, and that's called a black body, right? So we'll start by thinking about how black bodies emit radiation and absorb radiation, and then once we've got that kind of nailed down, we'll move on to how real surfaces do that, and we'll compare the real surface to the black body. So a black body is this kind of fictitious but really useful limit, right? It's kind of like a reversible process in thermodynamics in that you never really get there, but it establishes the best you can do, and so it's really useful. So a black body emits the maximum possible amount of radiation at a given wavelength and temperature, right? You'll never go above a black body. The other nice thing about a black body is it absorbs all the radiation that hits it, right? So we don't have to worry about anything being reflected. And then finally, a black body emits radiation uniformly in all directions, right? So that's what's called a diffuse emitter. So these are the characteristics of a black body. So this maximum possible upper limit is given by what's called Planck's law. So Planck's law is this equation right here. It gives you the black body spectral emissive power. So we'll come back and talk about spectral emissive power and what that means. But this equation is the maximum possible amount of radiation that any surface can emit at a given wavelength and temperature, right? So you can see that it is a function of wavelength and temperature, right? It's EB, my pointer being weird. It's EB sub lambda, so the lambda means it's a function of wavelength. If you look at this equation, you can see that it's actually a function of what wavelength and what temperature are you talking about. C1 and C2 are constants, they're natural constants, so this is a function of wavelength and temperature. All I did here is plot the black body emissive power, so this equation, as a function of wavelength, and then for, a bunch of different temperatures, right? So, if I plug 300 Kelvin into this equation and then plot the Planck's law as a function of wavelength, I get this curve. This is 500 Kelvin, 1,000 Kelvin, and so on. So there are a few things to look at here and try to understand. One thing that I hope is pretty obvious is that how much radiation a surface emits is a very, very strong function of its temperature, right? This y-axis here, as we go from 300 to 500 to 1,000, it's many, many, many decades of change, right? So, that's one of the reasons why when we are doing problems that involve heat transfer around room temperature, so down here at 300 Kelvin, a lot of the time we've been ignoring radiation as not being important. And part of that's because we're down here where the black body spectral emissive power is not really very large. But as we go from 300 to 500 to 1,000, the amount of radiation being emitted doesn't just go up by a little bit, it goes up by several orders of magnitude, right? So whereas we might be down here near room temperature and have convection and conduction be our dominant mechanisms, as we increase towards higher temperature, you're likely to get into regimes where radiation is your dominant mechanism and convection is not very important, right? So that's something to sort of understand from this, and that has to do with Planck's law and basically how these things behave. The other thing to notice here is that as temperature gets larger, the radiation, the amount of radiation emitted goes up a lot, and it goes up at every single wavelength, right? So these lines never cross. At every wavelength, more radiation will be emitted. Where the radiation emitted tends to be concentrated more and more at lower and lower wavelengths. So when I'm near room temperature, I will emit radiation out here at pretty long wavelengths. As I get hotter and hotter, I'm going to start emitting radiation down here at much shorter wavelengths, right? So, this peak and this curve starts to shift towards lower wavelengths as I go to higher temperatures. The peak in the curve is given by this equation here, which is called Wiens Law, right? So, at a given temperature, this equation will tell you where the peak is in terms of where that body emits the most radiation.